show you many of these plots later in the course. This plot shows you the difference between the real seismic velocity and the standard seismic velocity based on this average or reference Earth. Okay, so here in this picture, which is a slice of the Earth somewhere in the Pacific, with the Tonga arc being plotted there. This is one of the subduction zones. What you see here is that there are places where the color is blue, and that means that the seismic waves here are about 2% faster than the standard Earth. And on this side it's red, and in these places the seismic waves are about 3% slower. And we know from calculations and also from laboratory experiments that a warm mantle has a little bit lower seismic velocity, and the cold mantle has a little bit higher seismic velocity. So what this picture shows you here, based on seismic tomography, is the temperatures in the mantle. This is cold, and these places are warm. And what you can see here, this is a very famous picture published in 1997, so already 10 years ago, by a colleague of mine, Rob van der Hilst. It shows that there is this lithospheric plate that is going down into the subduction zone. The white spots are earthquakes. That's of course the Benioff zone that we all know. But he has shown that this plate goes down, and then it is resting a little bit on this 660 kilometer discontinuity in the mantle, and then it goes down and sinks until it is so warm that it cannot be seen anymore. A subducted plate is cold. It's colder than the surrounding, and that's why it has a higher seismic velocity. So using seismic tomography, we have now mapped basically the mantle. We have an idea where subducted plates are, how old they are, and so forth and so forth. This again can be compared with computer modeling, and I hope that this movie will work. Okay, so what you see here is a model of about 600 kilometers and 200 kilometers deep, the upper part of the Earth, and the color is the temperature. And what you see here is the boundary between something rather cold and something rather warm, maybe the boundary between a continent and the ocean. And at this particular point you start the subduction. Let me go back and show it to you again. So this material here is cold, and therefore it is heavy, and it wants to sink into the mantle. And here is the beginning, a computer model of the beginning of subduction. Okay. And the final movie to be shown here is from the group in Zurich, where now the colors are different kinds of rocks, showing you a subduction zone, and the lines are the lines of constant temperature. So on the left side you see a subducting plate, and what they have simulated here is this very, very complicated process of mixing above a subducting plate, forming a mountain belt. And nowadays very high performance computing models can actually track where a material goes in a zone like this. And again, what is very important for you to realize at this point is that these models are hard rocks. Earthquakes go right through them, but if you wait for millions of years, tens of millions of years, then they flow like soup. And that's why you are getting these pictures, which really should remind you of stirring your yogurt at breakfast time with a little bit of marmalade or something. all these processes that I've explained to you now can only be shown or can only be seen with very sophisticated tools to visualize. Okay, and so I put up this picture here. These are 4 different computer-generated images of our planet, and they are very intuitive, very simple to see. This is, of course, the topography. These are the volcanoes. This is the internal structure of the Earth, and these are the earthquakes. But just try to imagine what kind of powerful databases and computing power is necessary to give you these pictures. Okay, there is an instant engine to plot everything in the right place, to extract the kind of data that you want, and nowadays there are these 3-dimensional caves where you can go in and put up your glasses and really touch something in 3 dimensions. So the visualization of these processes has nowadays become a science by itself. There are people who just study visualization, develop techniques to show these enormous amounts of data that we have in ways that are intuitively easily understood. Visualization. At a much shorter scale, the visualization can become extremely graphic, and it will grip us basically every day. So tectonics at the human time scale is manifested by volcanic eruptions, by landslides, and so forth and so forth. This is a famous picture from Mexico showing the remnants of a landslide, and we will see more of such pictures. Of course, they are treated in much more detail in Klaus Reicherter's Neotectonics and Geohazards lectures. And another visualization closer to the surface, which really has a direct link to what people live and what they feel, is in the San Francisco area. And this is an online map that you can download if you live in San Francisco, but of course you can download it from Aachen too. And it actually shows you the risk of a big earthquake hitting your town or your area or your street within so many years. Trying to prepare people to make them make it possible for them to live in such a dangerous world, to know what kind of risks they are taking and what they can do about it. And again, these are powerful simulation and visualization techniques to calculate these risks and to base our expectations of what is going to happen on a really solid statistical foundation. The next big tool is tectonic stress. We have learned in the past 15-20 years to really measure stress in the Earth, especially close to the surface, say in the top 15 kilometers or so. And the picture that I made to show you this is a digital elevation model. Shows you the altitudes of India, and here there is this little beach ball. They call it a beach ball, and it is basically the solution of the seismic waves generated by an earthquake. So if an earthquake rips the earth crust, then seismic waves will go in different directions at different speeds, and if you record these seismic waves, then you can analyze them and reconstruct the way this fault has moved. And of course, we have learned in the mechanics parts of the lectures that if you move like this, then you have a normal fault, and then the vertical stress is the biggest one, and if you move like this, then you have a strike slip fault, and sigma 2 is vertical, and if you move like this, then it is a reverse fault, and the biggest stress is horizontal. And these beach balls basically tell you in which quadrant of this stereo plot the highest stress is, the sigma 1 is. And of course, earthquakes are all over the place. And nowadays, people in geophysics monitor earthquakes. There are many, many earthquakes every minute on Earth. And this is just a map that I downloaded from all the earthquakes on June 99. And what you can see that there are a lot of very small ones that nobody notices. And even on such a day, there is somewhere a rather big one, maybe a magnitude 4 earthquakes. Of course, a 5 and 6, a 7, 8 and 9 quake are much more rare. But basically the Earth is ringing all the time and providing us continuous information about its internal structure. The next very, very important tool has evolved over the past 15 years, and that is the GPS. All of you have used GPS nowadays. It's quite normal. You have it in your car or maybe even in your mobile phone. But there are uses of a GPS which you may not be familiar with, and that is to put a GPS on one place and leave it there, and then record the position of this GPS station over time. Here is an example